I'm going to make a recording of today's class. A few students are going to be out. If you ever find you're going to be in that situation, feel free to ask me. There is every once in a while a time when I can't do it just because I'm doing a lot of board work, but usually I can do it, okay? So always feel free to ask. Hopefully everyone's turned in exam 1. It's due now. If you haven't, please do that right now if you haven't turned in exam 1, okay? I want to go through a few announcements kind of quickly while you guys are doing that. So take-home portion is due right now. Everyone wants to turn that in. The online portion is due at midnight tonight. One thing that I'm seeing on the online that concerns me is people are taking a lot of time to do it. Some people are taking on the order of hours. It really should not take you hours. If you're prepared, really no more than half an hour, 45 minutes. It's actually designed to be doable along with the take-home part in one setting, in an actual class setting. Even though I give you an unlimited time, the reason why you want to heed this warning is when you get on the final, there is no extended time. It really is 2 hours. And if you're not prepared, if you're taking way too long on these online portions, chances are you're going to take way too long on the final, okay? So a word to the wise. All right. Extra SI sessions. So there appears to be some interest in having more SI sessions. And I think I threw out the possibility sometime in the past of having evening office hours. I'm willing to offer more office hours, but I'm willing to offer more SI hours sessions, but I really need your input. So if you're interested, go to this Google Sheets page. It's hyperlinked in the next line. This is in the announcements, okay? And what I need for you to do is I need for you in the second column to express your level of interest. So if you're not interested, just put a 1, okay, and then it goes from 1 to 5. This is called a Likert scale. Okay? If you would like to attend, but none of those days work for you, so I can't stay every single night, okay? So I think there's 4 nights that I'm able to stay. Let me know. Put a 99. That's a special indicator, all right? There is a pretty good chance that, and so in the things where you're able to attend, so if you don't enter a 1, in other words, you have some interest, okay, put an X on all the sessions that you would be able to attend. Would be able to attend, and leave the other ones blank. Okay. There's a very good likelihood I'll be able to offer the extra SI sessions. The only caveat is that, professors do things outside of class, and usually research we can kind of do whenever we want, but I'm an expert witness in a civil trial right now. And those things are like wild cards. You never know when work's going to pop up. So, I don't think it will be a big deal, but there may be 1 or 2 sessions where I have to fly somewhere or do some extra work and I might not be able to make it. But I'm pretty confident that won't happen. That's the only caveat. So if that happens, just be aware, and there's nothing I can do about it. So this is the handout that you guys have. And what we've been saying our goal is, we said that, okay, we want to summarize all the visual information. We want to summarize this big quantitative data set numerically. And then we want to describe it to someone else. So here's kind of the picture. We have to ask the question, what features of the plot do we want to describe? Now this is where you want to pay special attention, because the way most people do this is freestyle. They look at the plot and they write down what they think is important, and that's not how it works. So what we're interested in here is we're interested in what features are statistically important, okay? And it turns out that there's 3 specific features we have to look at. So here we're really looking at features that are statistically, and I got to apologize, I have to write on a tablet and I can't press really hard, so statistically important. And we're going to see that there are 3 such features, okay? So one of the things you have to do is kind of train your mind to realize that you don't say whatever you think comes to your mind. You have to kind of pick out the main things that are important statistically. Then we want to ask, what numbers do we want to compute from the data? And we already have a template for how to think about this statistically. So what what features that are statistically important. Yeah, I have to write on the tablet. My handwriting's bad. I can't type, so I apologize. Now, we already have a model for how to think about what we want to compute, right? And we talked about estimates, and we have this bullseye analogy, this target analogy. What are the two things we're interested in? We're interested in where is the data centered and how spread out the data is. And it turns out that that's what we always want to report. So the two things that we're going to be reporting numerically is what we call a measure of central tendency and a measure of variation. In other words, I want to give some measure of how spread out the data is. So we want to compute numbers that are going to tell somebody where the data is centered and how spread out it is. Okay. And of course, the last thing is we have to put all this together. You have to be able to communicate this. So this little cartoon where this individual's describing the way the plot actually is, and someone sees it totally different. You see, the whole goal of being able to describe a plot is that I can give you a verbal description without you seeing the data or the plot, and you can see it in your mind, or at least get a rough idea of what it looks like, okay? So that's where we're going today. Okay. And so these are the five. So it turns out that the things we describe depend a little bit on the plot we're going to make. This won't make a lot of sense right now, but we'll come back to this. This is just kind of a chart for your own reference. So you can see that we're going to talk about 5 different things. And how we describe them, there's some little variations for these different plots, right? The histogram, the box plot, and the dot plot. So the first thing we have to talk about are the number of modes. So this is the first thing that we report. There's 5 things we report. And the first is a number of modes. And what is a mode? Well, you have to be a little careful. So a mode, when you have categorical data, we said was the quantity that occurs most commonly, right? For categorical data, it's the category that occurs most commonly. For quantitative, it's not quite the same. So a mode here is really referring to the number of peaks. Okay, so what we want to report here, we're not so much interested in the location, we're interested in the number of peaks. And we think of a mode as like a local maximum, okay? If my handwriting's too bad, let me know. Now, one of the tricky things, and this takes a little bit of experience, is that you have to be able to distinguish modes from fluctuation in the plots, okay? We're trying to fit this plot to a nice smooth curve in our mind, right? But the data doesn't look like that. There's little jig-jags, right? There's little variations. So if you look at this plot, you might think there are 2 peaks, but there isn't. And how do you know for sure? What you do is, in your mind, you try to fit this with a smooth curve. And when you do, you can see that it's more likely there's 1 peak than 2 peaks. So this little blip is just a random variation. In other words, there just happened to be a little bit more in this bin than there were in this bin. One of the reasons why we don't give the value of the mode for a histogram is that there isn't one value, okay? The bin represents an interval of values. And it's also dependent on how you bin the data, okay? So it's not really meaningful to talk about, you know, where the mode is on a histogram so much. Okay, so this is what you need to be able to describe. So these are the different ways we describe the number of modes. It's possible to have no mode. This is a uniform distribution. Uniform in the sense of like a uniform policy, right? It applies to everyone the same. So in this case, all of these bins have roughly the same frequency. Now, beware. Again, you're never going to see a data set where they're all exactly the same. In fact, if you see it, you should be suspect, because the chance of that happening is minuscule. Good example of a uniform distribution might be if your train comes between 10 o'clock and 10:10, and it's equally likely to come at any time. or you roll a die and you look at the frequency of each face that comes up. Those are all equally likely to occur, right? Most common is unimodal. And again, you kind of try to fit this to a curve in your mind and you see a single hump. And that's the most common one. Now, there are times when you get what's called a bimodal distribution. So again, and I say this like 100 times, I know, in the class, but it's because it's so true. Things in statistics sound like what they are. Unimodal, uni means one, like unicycle, right? One mode. Bimodal, like bicycle, right? Two modes. And here you can see that the two modes. Okay. If you tried to fit that to a nice curve, it's too hard to really fit it with a single curve, okay? And again, you notice it takes a little bit of time and a little bit of judgment, okay? Like this one is unimodal, this one's bimodal. And we're going to talk about also ways you can go back to the data and actually kind of verify it's one or the other. And finally, if you have more than one mode, we call this multimodal. So this is a situation where there's a huge drop here, okay? It may be due to binning, but probably not. So we don't go crazy and start talking about trimodal, quadrimodal. We just lump everything into multimodal. And the reason why is it's so rare. If you have multimodal data, you have some serious issues, okay? So this is what we want to describe. The first thing you have to describe is a number of modes, and this is how you describe it. Any questions on how to do that, what we're trying to do here? Now, yeah, Darian.
If you're trying to explain that verbally, how would you say that there's peak and average values at, say, this band, like there's a peak and average age at 20? That's a good question. So we're going to use these terms. So we would just say it's a unimodal distribution. And we're not going to worry about the location. Unlike categorical, where we don't worry about the location because, first of all, there isn't really one location. It's actually an interval of values. And it's dependent upon how wide you make the interval. So it's not really meaningful per se. So I would just describe this as unimodal. That's all we're going to say, okay? All right. So let's look at this plot. This is a plot. This is actual data from 2008. This is the average drive of all professional golfers. So they had professional golfers like drive the ball 3 times. They took the average. Yeah,
What prevents just lowering the number of bins in the multimodal plot and getting one of the other?
That's an excellent question. So this is why it's called exploratory data analysis. So, for example, if I was going to look at this plot, if I was serious about looking at this plot right here, I would probably revise the bins. And when I found a bin width that let me fit it with the best smooth curve, I would take that.
And how do you know if the problem is the number of bins or how you collected data that is caused by that?
So we're gonna talk about that. So this isn't just like playing around where we're trying to. So it is playing around a little bit. We want to try to change the bins till we get a nice smooth curve going through. Usually the less peaks the better. If I can increase the bin width, which is what I would do here, I would increase the bin width. See if this kind of formed one mound, I'd probably take it. However, there's another way we can look at it, okay? And this goes to why this is statistically important. Why do we care about the number of modes? So this is the average drive of all professional golfers from 2008. Clearly bimodal. No one disputes that, undisputed. What do you think those 2 peaks represent? Who do you think are the golfers in those 2 different peaks? Maybe no, because notice there's a heck of a lot of people. I mean, there's a lot of people in here, and each person just have one average, right? What do you think?
Someone who golf.
These are professional golfers. They're all good at golf. No.
Age of golfers?
Professional golfers are usually like over. So there could be age, but I think there's a much more likely explanation. Well, male and female. Okay. People assume it's all male, but it isn't. It's all professional golfers. They're professional female golfers. So what do I actually have? I have 2 populations. Okay. So we would describe this as being bimodal. And each of these peaks represents a subpopulation, okay? And most likely the subpopulation would be gender, okay? So in general, this is what modes represent. So to go back to Luis's question, what you would want to do is you'd want to go back and investigate those people in the modes. Is there something about them that makes them different, okay? In this case, it's gender. We care about that because chances are I do not want to average, I don't want to analyze men and women together, okay? There are very few scenarios where you'd want to analyze both at the same time. I'd probably want to analyze each of them separately. So that tells me to actually split my data set apart, okay? My population's a little too big. Generally, this happens for two reasons. Either A, you don't think carefully enough. Like, for example, when I first looked at this, when I didn't know the answer, it took me a few seconds to figure it out, okay? So this person collected the data. They went to ESPN and just copied and pasted everything and wasn't thinking about it. Or B, sometimes there's an extra factor that you don't think about, okay? So like age is a factor that you might not think about, okay? Sometimes there's some lurking variables that are going to affect you. So that's modes. Okay, second thing we describe is shape. And again, we keep it really simple, okay? We don't try to be complicated. There are basically three types of shapes you can have in statistics. You can have what's called left skew. So skew, again, kind of sounds like what it's saying. The data is skewed to the left, okay? But skew in statistics mean tail. Code word for tail. So this is a data set that has a tail on the left. You can have right skewed distributions. So right skewed means right tail. There's a tail on the right. And finally, you can have symmetric. So there's a line of symmetry. In other words, you could find some value, cut it in two, and it's going to be relatively like a mirror image around that axis. Again, symmetry is never perfect. If you see something that looks perfect, you have to actually become suspect unless you have a huge data set. Okay. So usually what we're trying to do is we're trying to put the plot in one of these three bins, okay? So you can have a symmetric that does have a little bit of a tail, but if it looks more symmetric than right skewed, we're going to say it's symmetric. Sometimes people will say things like it has a slight right skew. Sometimes it's hard to tell. You might have a few beta values out here that look like a tail, then you can say slight right skew. But usually we don't try to put too fine a point on it. One of the things we want to understand in this course that's important is when do we get these different types of data sets? Like when would you get a left skewed data set? Notice what's going on. Okay, go ahead. Okay, so age is definitely something that is skewed. What would age be skewed as? Would it be left skewed or right skewed? How would it depend on the axis? Oh, it's always going to go small to large. We're working on a number one. Yeah.
Where are you sampling the age from?
Well, let's just say it's a general population. I take everyone in the U.S. What would it look like?
The U.S. it would look more older people than that.
I wish it was. I'm getting old, man. I sure wish that was the case. So you're going to have a whole lot of young people, right? The infant mortality rate is really low compared to the mortality rate when you get 60. So you get right skewed distribution when you get a whole lot of people bunched up at the bottom and a few here, okay? And these are things that necessarily you might not have really good intuition on in the beginning. But age distribution tends to be right skewed. Okay. There's one thing that's right skewed that's incredibly important for you guys. It's income distribution. Anytime you deal with any sort of financial data, so income, okay, when you deal with measures of human performance, these tend to be right skewed.
Think about income. What is all this stuff about the 5%? Well, it's 95% of the wealth is held by 5% of the people. It means 5% of the people are super wealthy, right? They're up here, and us plebes are down here. Okay, that's what that's referring to. But it's true in any sort of income distribution. You look at any organization, with very few exceptions. Most people make in here. Okay, Embry-Riddle's the same way. I make like down here, right? And the president makes like some humongous salary way up there. Okay, so it's true. It's true for any sort of income distribution. I'll just say this really quick because it's interesting. People think that this is a sign that there's some sort of inequality. It isn't. That Pareto distribution that we talked about when we studied categorical variables was developed by an economist. And he noticed this, okay? He noticed this in a really weird sort of situation and began to apply it. And he was Italian. And he made a really unfortunate observation. He made the observation that 80% of the land in Italy was held by 20% of the population. And unknowingly, Benito Mussolini picked up on that. And that was a really strong theme of his, that we should have communism or fascism. He didn't mean to do that, unfortunately. But he proved that this is a mathematical consequence of free market capitalism. It has nothing to do with the inequality. Of course, when it gets too skewed, maybe there's something wrong. But this sort of inequality occurs naturally, okay? All right, symmetric data, but here's what I want you to take home. Income. Any sort of financial data is always going to be right skewed, almost always. Okay, symmetric. What sort of data is symmetric?
Average grades.
Sometimes. But standardized exams are. So GREs, right? SATs, ACTs, all those T's. Right. What else is symmetric, you think? There's one that's really important. It's deviation from manufacturer's claims. I know it doesn't sound too exciting, but when you go to the store tonight and you buy like Raisin Bran or hopefully something a little healthier, and you see 16 ounces on the box, there's not 16 ounces. Everyone knows that. There's going to be deviation. Those deviations from the manufacturer's claim end up having a normal distribution. And actually, part of what I'm doing as the expert witness is actually dealing with this. So someone made a claim, and the actual data point was way over there. So they're way, way off. So people like Morgan and these guys, they have lawyers that do this sort of analysis. This is how class action lawsuits get started, okay? So that's really key. Here, I'll put it in red to make it really dramatic. Deviations from manufacturer's claims.
Did you also call that tolerances?
Tolerance is another way of thinking about it. That's right. Yeah, any sort of claim about performance, the deviation generally should be symmetric. Okay, there are some exceptions, but not many. There's one last one that's really important for this class and you in general. It's any sort of measurements taken from human beings. So height, weight, blood pressure. Okay, so to be really precise, we're going to call these physiological measurements. Oh, claim, C-L-A-I-M, sorry. C-L-A-I-M. Physiological, where am I? Physiological measurements. Okay? So height, weight, IQ, although that's more psychological, but those are all. And those are the three that I would expect you to know. Like on an exam, if I give you a data set and these things were on there, okay, I said like this is blood pressure. You're supposed to know that blood pressure has a symmetric distribution. That's going to be implied, okay. Left skewed is actually relatively rare. Who can think of an example of a left skewed variable? Yeah.
Attendance at a bar.
Attendance at a bar. Okay, what is the variable here? What's that?
Yeah.
Okay, so you'd be saying.
I'm thinking like number of people as the night goes on, as time goes on.
That's actually, so that's a little bit different. That's more like a cumulative sum. It's a little bit different. But where would be a situation where there'd be a whole lot of people bunched up at this end and very little at this end? There aren't many, actually. Death rate. So death rate's the obvious, okay? And I don't expect you to know this, okay? I expect you to be able to figure this out. But death, the age of death, call this death age. If you look at the SAT scores at Harvard, SAT scores of Harvard have this sort of distribution. The vast majority of people score above 700. A few people score down here. There was one other I wanted to say. I can't remember. It'll come to me later. But this is actually, I won't say it's rare, but this is not that common. Oh, okay, so here's the sort of thing I would expect you to figure out on an exam on your own. Suppose our quantitative variable is the time it takes a student to complete a test. What would the distribution of test times be if the exam was easy? And what would the distribution of test times be if the exam was hard? Those are both skewed in a different direction, okay? So that's one to think about, right? So here's one to go home and think about. If our variable is the time to complete a test, what would the distribution be for a difficult exam? And the way you want to think about this is, where are most of the values bunched up? If it's a difficult exam, are there a lot of really long test times or short test times? Long, right? So here you're going to have a left skewed distribution, right? A few people finish real early, most of the people take a long time. If it's an easy exam, it's going to be the opposite, right? A lot of people are going to finish soon. So wherever the majority of the people are, that's going to help you figure out where the skew is, okay? Now, unfortunately, I can't tell you why shape is important right now. We got to talk about the center and the spread. We'll come back to this, okay, why it's important. But right now, we're going to skip over that. Okay. So any questions about shape? Yeah, Gary.
No mode for it's zero mode. How is that symmetric? Just because it's flat plus and straight down.
Symmetric. That's right. So if you have a uniform distribution, I can go to the middle of that, cut it in half, fold over. Yeah, and so that's an interesting point. So uniform is always symmetric, always.
And even if it's not exact, as long as it's close enough, that's fine.
And that's the thing. So we're trying to put them into bins. Like, what does this look like more? And it takes a little time. It's not something that everyone will like get right away. So if you don't get it, don't fret. Okay, you will.
If you have basically a linear curve that say starts at 100 and moves down to 0, and it's just a straight line, would the 100 be the peak, even though it starts at like 0 of the?
Yeah, if you had a distribution. So you're saying, I'm sorry, 100 here, and it goes like this?
No, other way around.
Okay, like this?
Yeah. So that would be the peak up there, even though it's not a curve.
That rarely happens because data doesn't follow a nice perfect. Yeah. So you'd say it was unimodal, it would be a right skewed. So most likely in real life, it would look like this. This is one of the reasons why I use real data sets. If you use book data sets, you'll see that. But in real life, you only see that where unicorns live and all that stuff, right? Okay. So outliers, what are they? We already know. They're data values that are separated from the rest of the data. That's how we want to think about it intuitively. So these are data values that are separated here, separated from the rest of the data values. Okay? Think of outliers like outcasts, right? The rest of the data wants nothing to do with them. They're far, far away, all right? What do we do with them? Anyone remember from chapter 4, way back? If you use a trim data set, that's what you're going to do. If you don't use a trim data set, what do you have to do?
Look at them to see if they're relevant or not.
Yeah. So the relevant issue is you have to see whether or not they're from the population that you're interested in. Okay, you can convince yourself they're not. Like we gave that example in class of apartment prices that a student was looking for, right? And there was that one that was like $5,000, but the student was looking for reasonably priced apartments. That wasn't in our population. Okay. One thing to be careful about, and students miss this routinely. There's a difference between invalid and outlier. What is the difference? Madeline, what is the difference between invalid and outlier?
Invalid is where you do the math wrong and you know that can't be evaluated as an outlier is just one that doesn't fit the rest of the data. Right, so invalid is one that is impossible. It can't happen. You can't have a height of -5 meters, okay? It's impossible. So obviously there was an error of some sort, right? Okay, how do we detect them? This is tricky. And what this is this is the home run totals back in 1920. So in Major League Baseball, you go on ESPN, you pull up the home runs that every player hit, right? And this is the box plot. Weird looking box plot, isn't it? Like the box is this wide, okay? Now, here's the question: are all of these outliers? The box plot says they are, but they aren't, right? Sorry about that. Just turn down the volume. That'll work. Okay. Are all of these data? So remember how a box plot indicates outliers? It puts little dots there, right? Are all of those things outliers, though? And why? So the answer is no. The reason why is when you look at the histogram, you see that these guys are actually part of a long tail. That's one of the strengths and weaknesses of a box plot. A box plot will indicate things that can be outliers. It'll indicate all the potential outliers. But in this case, we would call these outliers in name only. That's not a technical term, that's my term, but that's how people think about these. These are not outliers. These are just part of a really long tail. And it just happens the box plot is so small, and you may or may not remember this, we talked about how there's like a fence length if you go beyond the box. That box is so small that fence really isn't that wide. So these things appear to be outliers, okay? So Babe Ruth was the only outlier. This is back in 1920. He hit 54 home runs, okay? And these are outliers in name only. Again, to go back to Luis's question before, this is why it's called exploratory data analysis. When I make plots, I make a box plot and I make a histogram. Because if I just make a box plot, I'm going to come to some erroneous conclusions here. Okay, so you really want to do both. How do we interpret outliers? We've already talked about how outliers are part of a different population. But is Babe Ruth really part of a different population? Like, is he an alien or something? Or, they didn't have steroids back then, right? Yeah. I'm sorry, can you say it a little bit more?
You see if that person or that population is from the one that you're interested in. So if most people only one that they're interested in,
But he is from the population I'm interested in, right? I really am interested in all the Major League Baseball players. Any ideas? This is one of the most important things about outliers. That's why you don't believe them. Outliers can indicate a trend. Okay? That's super important. So outliers, they can be part of a different population, but they can also represent trends. Let me show you something. So this is the home run totals from 1920 and 1927. So here you can see this is a histogram of all the home runs in 1920. The second highest person hit 19 home runs. Babe Ruth hit 54. He hit more home runs than every single team hit together, okay? And you can see this here, right? He's an outlier. This is part of the tail, right? Now, fast forward to 1927. What happens? Well, Babe Ruth is still hitting a lot of home runs, but he isn't as dominant anymore. So Lou Gehrig hit 47, Roger Hornsby. These guys are hitting a lot more. You can see that really what's happening now is he's beginning to start to become part of the tail. He's the start of a trend. You see this in athletics a lot. Nobody could break a 4-minute mile for the longest time
then all of a sudden, Jim, I think it's Ryan, I want to say, broke it, and like everyone after that. The bar is raised, and somehow everyone's doing that. You see it in bodybuilding with people, all of a sudden there's phases where guys get super huge. Any sort of sport you can think about. In business, it also happens. You see trends. Google is definitely a trend, okay? There are a lot of businesses that come up with brand new ideas, outperform everyone else, okay? Then everyone else catches up. So there is a really cool book that I'll plug. It's called The Black Swan, and it's written by an economist called Nicholas Taleb. He's kind of a little arrogant, but the book is really good. Homeland Security has to worry a lot about outliers. And this book, Black Swan, is about things that no one has seen before. So like 9/11 was something that no one had seen before, right? So the question is, how do you anticipate these sorts of events? How do you build these in? Sometimes the outliers are the most important things, okay? So outliers are fascinating. That's why we do not just throw them away. So what do we do with outliers? How do we report them? Usually we say the number of outliers and we say their position. So if I wanted to describe this data set from 1920, I would say it's unimodal, right skewed, with one outlier at 54. Okay? Okay?
Name how many outliers you know there are.
Yeah. So usually we give.
If there's more than one, would you group them as like they're in this section of the data, or would you name them that?
Well, the outliers are generally going to be, I mean, usually when you encounter outliers, you also have skewed data sets. So if there was more than one, I'd say there are 3 outliers at 54, 68, and 70. And then, the person has to look at the data to see those. Yeah.
What we're talking about outliers that would be invalid. You have to look at that one.
So outliers are values that are extreme but could happen. So you could have a person that's 7 foot 7 inch. It's really unlikely, but it could happen. You can't have a person that's 10 feet. That would be invalid, right? So sometimes you have to give a little bit. Sometimes you have to do a little bit of research. So this is why, again, it's called exploratory data analysis. So a really good example. If you remember, we talked about outliers. We had a data set with a number of children in each home. And there was one home that had 99 children. And we said that was invalid. It might not be. What if it was an orphanage that they went to? Okay? You don't necessarily know what the other person is doing when they do the data. Then it would be an outlier. It wouldn't come from the population, and you would still remove it. So sometimes you have to know a little bit about context. But usually, when it's an outlier that's not in your population, and invalid, the result's the same. You're going to remove them anyhow. So sometimes it's just a distinction in name only. Okay. Okay, so now we're going to talk about the center. And it turns out there are 2 different ways we can measure the center. Okay. We talked about that target analogy, right? We want to know where's the data value centered around. By the way, one really quick comment I want to make. A lot of people on activity 3 said the larger the data set, the more it's centered around the true value. That's not right. It can be biased, okay? So we don't know where the data set's centered around. It might be centered around the parameter, might not, okay? But in any case, we're interested in where it's in the value it's centered around. And there are 2 different ways that we can measure the center. So the first is the average or the mean. Everybody knows how to do that, right? You guys have been doing that since 5th grade. Take all the data values, add them up, and divide by the number of data values, right? So this is mu hat, the sample mean. Or we can have a population mean, either one, right? The median is also another good way to measure the center of the data set. So we talked about the median, right? Order all the data values and find the middle data value, okay? Now, so this is where we get a little bit tricky. So what does the center actually mean? Now, when you have a symmetric data set, you can use either one. It doesn't matter. If you think about it for a second, if you have a symmetric data set, this should be the 50th percentile, right? I mean, and you can see this in the plot. That's what symmetry means, right? There's 50% on one side, 50% on the other, because it's a mirror image. And of course, the mean's going to be the same, because every value this far away is going to be an equal number of values the other direction, and they're going to average out, right? That's not an issue. The question is, what happens when you have a skewed data set? This is where we have to be careful. So I want to give you a hypothetical example, okay? So suppose I run a plant and I produce clothes in an undeveloped nation. I have 9 workers. I pay each $1. I pay myself $991. And in social media reports that I run a sweatshop. And so what do? I get together with my PR team. I say, no, you got it totally wrong. It turns out that the average salary of every one of my plants, $100 an hour, even for America. That's a tremendous salary. I'm a terrific guy, right? Am I? Well, one of the things we want to think about in this class is what is true versus what is deceptive. So let's first of all figure out if I'm telling the truth. So if we compute the mean, what are we going to get? Well, I'm going to average them up, add them up, right? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 people making $1. I'm making 991. I have 10 employees. So sure enough, that averages to $100 an employee. I'm telling the truth. I'm not lying. You guys have all heard this phrase, statistics don't lie, but liars use statistics. A classic example, right? What is the median of this data set? James, what do you think? The middle value. Where would it be? Yeah, exactly. See, statistics just like it sounds. So I have 10 data values. The 5th and 6th data value are the middle data values. I take the average, the median is $1. Okay? Let's look at the data. If I plot the data, if I make a histogram, right, I have 9 people making $1, and I have 1 person making $991. Not drawn to scale, right? This is the mean. This is the sample mean, right? And this is the median. The median doesn't really have a symbol. Some people use capital M. I can't see the point of introducing another symbol. Okay. Which should be the center of the data set and why? Remember what that target analogy is kind of looking at? What do you think? What do you think, Tariq? Which way are you going? $1 or $100? Which should be the center? Okay. Adriana, what do you think? What's that? I'm sorry. Median. The median. Why? Yeah. That's the idea behind the center. We want to pick the data value that most of the data values are centered around, and that's actually a nice way of putting it. That's the value that's actually representative of what I'm paying, right? So this is how we think of the center. So the center is really the value that most of the data values are centered around. When we have skew in a data set, or we have outliers, they act to pull the mean out. The mean's no longer representative, okay? And that's what's happening. If you didn't have the 991, the mean and the median will be the same. That 991, it's an outlier in this case, is pulling the mean out. That's not always true. Sometimes people say it's always true. It isn't. But for financial data,
the sort of skewed distributions we have, it tends to be true. So when we have outliers, it's best to use the median for just the reason that you saw. That 991 is an outlier. It's valid, right? But it's definitely an outlier. And it's skewing, okay, in the sense the mean. So we're going to use the median, okay? We say it's resistant to outliers. When we have skew, we use the median. And let me show you why. I'm going to show you a really quick example. This actually happened historically. How many people know who Scott Boras is? Okay, Scott Boras is the top sports agent in the world, okay? This is one of the ways he got his reputation. So if you look at Major League Baseball salaries, at the beginning of free agency, that's when they let the players kind of leave on their own and find their own team. What happened was the salary started going up because there was a lot more bidding for the top players. So if you look at the average salary after free agency, you can see it's really increasing because that white skew is kicking in. Essentially, they're that free market capitalism, okay? And if you look at the distribution of salaries, you can see what happens. The mean's getting pulled out. The minimum did not change very much, okay? And what Scott Boras did was this. He was a very clever individual. He was an attorney by trade. He noticed this discrepancy. And I believe back in, this was 86, I want to say, he was negotiating for a Baltimore Orioles shortstop. And he went to the management, and the guy's name was Mark Belanger, if I remember correctly. He said, my shortstop's an average player. And everyone said, yeah, he's an average player. So he should make the league average, right? Yeah, he should. Because the center of the data set was 235,000. That's what he should have been making. That was actually representative of most of the ball players. The mean was almost twice that. He didn't get 430, but he got a really good price, got well more than 235,000, okay? And he did this for 2 years. And the second year he did it, I forget, there were 4 teams involved he was negotiating with. But the second year, some of the teams figured it out. The reason why they didn't was because salaries were so far out of control, people just thought, well, that's what's going on. Even though they're good at numbers, they didn't really think about what was actually going on. They didn't look at the data. And the second year we tried it, some of the teams said, he's really kind of in the middle, right? And I said, yeah, well, this is really what the middle is, so he's getting this, okay? In the third year, all the teams figured it out. And he couldn't use that. But this thing happens a lot. So for example, when you're looking at houses, okay, house prices of anything, commercial goods are always right skewed. If you think about it, think about your own neighborhood. Most of the houses are kind of average, a few are really nice, right? Consumer goods, phones, cars, right? Most of the cars are kind of in the middle. There's a tail of really expensive cars. Houses prices are the same way. So when the realtor is trying to sell you a house, what do you think they're going to tell you? The mean or the median? They're going to tell you the mean because they want you to think you're getting a really good deal because the mean's inflated and you think you're moving into a really good neighborhood. When you want property taxes assessed on your property, what are you going to argue when you go to City Hall? For the mean or the median? I'm going to argue for the median, right? Because I don't want to pay as much. The median's less than the mean, okay? So people use this sort of stuff, sometimes inadvertently. In the case of Scott Boras, there's little doubt he did that intentionally. He knew exactly what he was doing, okay? But a lot of times people do it unintentionally, okay? They just think the answer is always the mean, and the answer is no, it's not. Okay, so this is a nice little chart to have. We're going to talk about this last thing, which is called the spread of the data set. There are 3 different measures of the spread. The first is the range, and the range pretty much sounds like most people think it is. It's just the largest minus the smallest data value. It's the interval that contains all the data, okay? The interquartile range, we already talked about. It's that length of the box. It's Q3 minus Q1, all right? The standard deviation we haven't talked about. And this is the symbol for standard deviation, sigma. So this is an important symbol. So sigma is the symbol for standard deviation. Bless you. So this is the Greek letter for lowercase s, so sigma, standard deviation. And I put a hat on it, which means what?
Sample. Doesn't mean he's cold. It means it's a sample. Yep, standard deviation. And the way we think about it, I'm not going to get into this huge formula. The way I want you to think about it is a standard deviation is a measure of the average distance of the data points from the mean. So you think a mean is like home base, and standard deviation tells you on average how far the data points are from home base, okay? Notice that when we use them for very different sorts of data sets. When it's symmetric, we use standard deviation. We have outliers or skew, we use the interquartile range. When we have a dot plot, we generally can't estimate either of those really well because we have less than 20 data values, so then we give the range, all right? Now, there's kind of a notion in statistics that's important. So remember what it is we're trying to do when we're plotting the data and everything. We're trying to get an idea of what the population looks like. We're calculating these things like the center and the spread, and they're really proxies or approximations for what the population is, right? Now, the reason why I bring this up is because when we compute numbers like this for the center or the spread, we don't want them to be sensitive to single data values. Okay, we have in our mind this notion that the population parameter is relatively stable. A single data value shouldn't change it a lot. And with that in mind, why is the range a bad measure for the spread? It's easy to compute, okay? It has some information, but if we had a large symmetric data set, why would the range be or especially if we had a skewed data set, why would the range be a terrible measure for the spread? Well, the range is the most sensitive to the most extreme values, okay? So if you go back and you look at that data set with that sweatshop example, the range is what? 991 minus 1, okay? And again, that's $990. But remember what we're thinking about when we're thinking about the spread. Go back to that target analogy, right? We really want to know on average how are most of the data values distributed around the center. So 990 is not a measure of, on average, how far the data values are, right? It's really being skewed by that outlier, okay? So we don't use the range except for a dot plot. Okay, so last thing I want to do, this is a little story, win with the story. You guys all know Jack and Jill, right? So they became good old American assassins, okay? And Jack and Jill, you know, they fell down the hill. Jack still has issues with Jill and everything, right? So he's talking trash about her. He says she's a terrible shot. And Jill says, well, let's have a contest. Let's end this, right? Okay, fine. So they go to the shooting range, right? You guys have seen these sorts of things at carnivals, okay? And Jack goes ahead and he takes some shots, okay? So he's 6 centimeters off this target, 3 centimeters below, 4 centimeters above, 5 centimeters above. And Jill's pretty much spot on, okay? 0.4 centimeters minus 0.1, okay? And so she leaves and thinks, well, that's it. He's done. He's not going to say anything else. And then she looks on her social media feed, and Jack says, well, we had to shoot out. Jill wasn't bad. She was 0.2. She had an average of 0.2 centimeters off target, but I had an average of 0. So I guess I'm still the best. All right. And of course, Jill gets really pissed, right? Okay. So first of all, this goes back to this question of, is he lying? So it turns out, if you actually look at the data, he isn't lying. He's actually right, okay? It turns out that his center, if you look at it, the average actually is 0. And Jill's average actually is 0.2 off, 0.2 centimeters off. But is he being misleading? Absolutely. This goes to show that the center alone doesn't tell you the whole story, okay? This is why you need to know the spread. So notice that they each have kind of a symmetric distribution, okay? And you compute the standard deviation, and Jill is 0.67 centimeters off, and Jack is 6 centimeters off. Okay. So even though his average is actually 0, okay, his shots have much more spread. If you're going to hire somebody, right, you'd want Jill. I mean, she might not hit like exactly the heart, but she's going to take him out, right? Whereas like Jack might hit the person next to him, okay? All right. So this actually goes to a really important point. Why do we care about the spread when we're in business and stuff like that. I mean, why do we care how spread out our data values are? You go into a Walmart in any major city, everything is always in the same place. You go to McDonald's, they serve you the same crappy cup of coffee in every single location. Tokyo, England, or New York City. Doesn't matter where you go in the world. Why is that so important? Well, spread has to do with reliability. Okay. So the whole point of business is you always want to give people an experience that's very similar to each time you go. Right? If you're giving, for example, if you have like wait times for people in line and they're really spread out, you might think, well, that's really great. Some people don't have to wait very long. But guess what's going to happen? The people that do have to wait a long time, what are they going to do? They're going to do a lot of things, and one of which is, they're going to go on social media, and they're going to, say bad things about you, and that does influence people. Okay, so the key here is that standard deviation has to do with reliability. If you look at brand A and brand B, so we'll end on this point right here. So here's two different brands of paint, and you're testing to see how long each one lasts. Okay, so this brand A, the first batch lasted 10 months, 60 months, 50 months, 30 months. Brand B, 35 months, 45 months, 30 months. These are different batches, right? Which brand should you recommend to your boss, brand A or brand B? What do you think, Pat?
I'll say brand B.
Because it's more consistent, okay? So people when they buy your product, they want to have some measure of reliability. They want to know it's at least going to last this long, right? So this person, he had a great experience. This person had a bad experience. This person may not say anything. This person's pretty likely to say something, okay? They're not going to be happy. If you know how much it costs to paint a house, 10 months is not very long, okay? So if you look at businesses, how important it is, McDonald's is the most consistent. How many people saw that movie with Michael Keaton about McDonald's? You guys never saw it? It's a really good movie, by the way.
The one where you eat McDonald's every day.
No, not Super Size Me. It's about the history of McDonald's. And the whole point of McDonald's, the whole essence of McDonald's was they standardized everything. And you can see how important it is. McDonald's has more revenue than all of the other 9 burger chains combined. Okay. Now, obviously, they gained a lot of market share. They held on to it. But the reason why they held on to that is because of the reliability. So when you go to McDonald's, you know exactly what you're getting. And if you watch Super Size, you'll find out exactly what that is. Okay. So last thing I want to do really quick, and this is something that you should do. I'll go through it quickly because we don't have a lot of time. This is the F16 data. So I want to think about how I'm going to describe this, right? So I'm going to say that it is unimodal. Is it symmetric or right skewed or left skewed? What do you think? Right skewed. No apparent outliers. What should I use for the measure of the center of the data set? If I have a skewed data set, do I want to use the mean or the median? I want to use the median. So what I would say is the center is given by the median, which has a value of, and you'd have to go back and compute that. I'll let you do that. And if I go back and look at the spread, okay, this chart tells me that when I have a skewed data set, I should use the interquartile range. Okay, so you can use this chart as a guide for which measure the spread. So we would end by saying the spread is given by the interquartile range, which has a value of, try to write it up here, by the, you can just use IQR, which has a value of
You don't just say the spread is given by and then the number, because I have no idea what that number is, right? I don't know if you use the range, the standard deviation, or the IQR. So you have to say what it is, okay? And there's some slight variations, but that's pretty much how we want to describe it. For a box plot, usually we give the 5-number summary. Let me ask you a question. Can you tell what the skew is from this box plot? These are the same data set, by the way, and they're not quite put on the same scale, unfortunately. But can you tell? How can you tell?
The Q3 to Q or Q3 to max is slightly larger than Q1 to min.
Exactly. So 2 things you want to look at. You want to look at the position of the median. Notice that it's a little more this way. So that's suggesting that the data values are bunched up, right? In other words, there's 25% here and 25% here. So it's suggesting it kind of looks like this. And you want to look at the length of the whiskers. So longer whiskers means you tend to have a skew, and they should be consistent. When this tail is longer, this box should be moved inward a little bit, okay? What can't you tell from a box plot? We have modes, outliers, we have shape. We can tell shape, right? We can tell outliers. We can tell center and spread. I have the center and the spread. We can't tell the number of modes. And that's a weakness of box plots, right? In other words, it's very possible that this thing actually has 2 humps. So remember, the box plot's the lowest level resolution, right? So you lose that. You lose that information. Dot plot, very little you can describe. The max and min, maybe a rough shape, maybe the center, okay. Because you just don't have enough data points to make out that nice smooth curve. And man, we're just 1 minute over. Isn't that terrific? Okay. I will post the video if you want to go back and watch it. This is a lot to take in. Strongly recommend you go back and read the chapter, okay? This is a really important chapter. All right, thanks.